Why is Gibbs free energy often confused with other potentials? Imagine trying to find your way through a maze and confusing one term for another. That's similar to how scientists sometimes mix up Gibbs free energy with other thermodynamic potentials. These terms sound alike because they all describe energy in a system, but each has its own special role. Thermodynamic potentials are like different maps. They help us understand how systems behave under various conditions. The main ones include internal energy, which is the total energy inside a system, and enthalpy, which accounts for heat content at constant pressure. Then there's Helmholtz free energy, useful when temperature and volume stay the same, and Gibbs free energy, which shines brightest when temperature and pressure are constant. The reason for the confusion is that these potentials are connected through mathematical operations called Legendre transforms. These transforms change the variables we focus on, like switching from volume to pressure or from entropy to temperature. Because of this, the formulas for these potentials often look similar, involving terms like internal energy, entropy, temperature, pressure, and volume. When you see the formulas, it's easy to think they're interchangeable, but they're not. Each potential applies best under specific conditions, which can be confusing if you're not careful. Another reason people get mixed up is because of the phrase free energy. It sounds like a general term, but in thermodynamics, it's a specific concept. Gibbs free energy measures the maximum useful work obtainable from a process at constant temperature and pressure, excluding expansion work. Other potentials, like the Helmholtz free energy, relate to different constraints, such as constant volume. So the context matters a lot. People also often confuse Gibbs free energy with other potentials because they all include similar terms. For example, both Gibbs free energy and enthalpy involve the total energy plus pressure volume work. Their names and formulas overlap, which makes it easy to mix them up. Plus, the idea of spontaneity, whether a process happens on its own, is tied to Gibbs free energy. A negative change in Gibbs free energy indicates a process will happen spontaneously at constant temperature and pressure. But other potentials have their own rules for spontaneity, which can add to the confusion. In summary, the confusion comes from the close mathematical relationship between these potentials, their similar formulas, and the overlapping terminology. Each potential is designed for different conditions and tells us different things about the system. Recognizing these differences helps us pick the right tool for analyzing chemical reactions, phase changes, or other processes. Understanding when and why Gibbs free energy is the best choice makes it easier to see why it sometimes gets mixed up with the others.